Hello, my name is Tyler Hayes, and I am a current PhD student at the Rochester Institute of Technology in Rochester, New York. Today, I am pleased to present our work, Remind Your Neural Network to Prevent Catastrophic Forgetting. Code for our model is available on GitHub, and a link is provided at the bottom of this slide. Although humans are able to continuously acquire new information throughout their lifetimes, deep neural networks struggle with this problem. When trained on non-stationary data distributions, deep neural networks catastrophically forget previous knowledge. Moreover, neural networks are unable to immediately learn new information. In lifelong learning, we require agents to overcome these challenges while also being subject to severe memory and time constraints. This enables new online applications such as robotics, home appliances, web agents, or automatic speech recognition. Within the field of lifelong learning, there are two different training paradigms. The more popular paradigm is incremental batch learning. At each time step, the learner receives a batch of data consisting of one or more classes. The learner then loops over this batch until it has been learned and is subsequently evaluated. While popular, this paradigm comes with several caveats. First, the learner must wait for a batch of data to accumulate before it may learn, and looping over a batch several times makes learning time-consuming. Moreover, the learner can only be evaluated once a batch has been learned, which can be prohibitive in scenarios where decisions must be made immediately. The second training paradigm is online streaming learning, which overcomes the limitations of incremental batch learning. In streaming learning, the agent receives training instances one at a time, it is only allowed a single look at each example, and it can be evaluated immediately after learning a new example. This paradigm is closer to how humans and animals learn and is better suited for real-time learning. Regardless of the training paradigm used, conventional neural networks suffer from catastrophic forgetting of previous knowledge when updated on non-stationary data distributions. One of the most effective methods for mitigating forgetting is replay or rehearsal. In replay, previous training examples are stored in a memory buffer. When new training data arrives, the new and old data are mixed together and used to fine-tune the network. When using replay, two questions arise. The first is what data to store, and the second is how much data to store. While storing all previous data overcomes forgetting, it is not computationally or memory efficient and may not be necessary. Recently, researchers have been working to maximize the efficiency of replay. Typically, a fixed number of raw images are stored per class to enable representation learning, and performance is further improved by use of a distillation loss and more data augmentation. However, storing raw pixel images in a buffer is still memory intensive and is not biologically plausible. In fact, there are two major gaps between biological and artificial implementations of replay. The first is that hippocampal indexing theory postulates that the hippocampus stores compressed representations of data, which are reactivated during replay. These compressed representations are usually high in the visual processing hierarchy. This differs from current replay implementations that store raw pixel representations in a replay buffer. The second gap is that animals engage in immediate online streaming learning from non-stationary data streams. This differs from recent incremental batch learning methods, which operate directly on batches of data instead of learning samples one at a time. To overcome these limitations, we propose the Remind model, or replay using memory indexing. Remind is inspired by how the mammalian brain performs online streaming learning and consists of two key ideas. The first idea is to store compressed representations from an intermediate layer of a neural network for replay instead of raw pixel images. This more closely aligns with hippocampal indexing theory, and we implement the compression using product quantization on the mid-level CNN feature maps directly. The second idea is to control the stability and plasticity of the network by freezing part of the network. This is more consistent with how the brain updates high visual processing areas and reuses more general low-level features. More specifically, after an offline initialization stage of the network and product quantizer, we train Remind in the streaming setting as follows. Given a new training example, we first pass it through the earlier frozen layers of the network to obtain an intermediate feature map. We then quantize the feature map using product quantization and store its compressed representation in our replay buffer. We then reconstruct a subset of old examples from our replay buffer and mix them with the current reconstructed example before training the plastic layers of the CNN for a single iteration. During inference, we quantize the test examples and push them through the network to obtain predictions. We evaluate the effectiveness of Remind on the ImageNet and Core 50 image classification datasets. We then show that Remind easily generalizes to other tasks by pioneering streaming visual question answering. First, we present our image classification results on the ImageNet 2012 dataset. On the left, we compare Remind to recent state-of-the-art models designed for incremental batch learning in both the batch and streaming paradigms. For batch models trained in the streaming paradigm, we set the number of epochs to 1 and allow them to use a mini batch size of 50 previous samples, which is consistent with how Remind is trained. All models are allowed to use the same amount of auxiliary memory, which allows models like iCarl, Unified, and BIC to store 10,000 previous raw images, and Remind to store over 900,000 compressed representations. Overall, we see that methods designed to operate on batches perform poorly in the streaming paradigm, with severe drops in performance. Remind outperforms all methods in the streaming paradigm and is only 1.9% below BIC, which is the best model trained with batches. On the right, we show the learning curve for all models trained in the streaming paradigm. Overall, we see that Remind achieves the best performance, with SLDA, another model designed specifically for streaming learning, performing slightly worse. Next, we ran a series of experiments on the Core 50 video dataset designed specifically for streaming learning. Although replay has been one of the most effective methods for mitigating forgetting, regularization methods that constrain parameter updates have also received much attention. These regularization models are run in the multi-headed paradigm, where task labels for each batch are provided to the model during inference. This makes the incremental learning problem much easier. Regardless, we compared Remind against several recent regularization models when task labels were provided and when they were withheld. Overall, we saw that task-aware regularization methods performed poorly when task labels were withheld during inference. Remind achieves the best performance in both settings, further demonstrating its robustness. We extend Remind to streaming visual question answering, or VQA, in which an agent must answer natural language questions about images. In streaming VQA, the input stream consists of image question pairs. The agent must then produce an answer to the question about the image. Since the order in which the inputs are streamed into a model can impact its performance, we studied two different data orderings. The first is where all of the data is randomly shuffled, or IID, and the second is where inputs are organized based on which question type they belong to. We evaluate streaming VQA performance on two datasets. The TDIUC dataset is composed of natural images organized into 12 unique question types ranging from simple object recognition to complex counting, positional reasoning, and attribute recognition. We use TDIUC to test a model's generalization capabilities. The Clever dataset is composed of synthetically generated images and organized into 5 unique question types. Clever tests for multi-step compositional reasoning. We compare Remind against a simple fine-tuning baseline and the Extreme and SLDA models designed specifically for streaming learning. We found that Remind outperformed all baselines on both orderings of both datasets. However, Remind achieved strong performance on the Clever dataset when it was organized by question type. We hypothesized that the question type organization might be serving as a natural curriculum to aid Remind's learning. In conclusion, we proposed the Remind model for online streaming learning. Unlike existing models, Remind stores compressed, mid-level CNN features for replay. We demonstrated Remind's performance on the ImageNet and Core 50 classification datasets. We further extended Remind to streaming visual question answering and achieved strong performance. Finally, thanks to my co-authors for their contributions to the project, as well as our sponsors for funding the research.